Tonight, we're going to sit with one of the strangest empirical results in modern physics. The deepest theories we have, the ones that describe the cosmos to extraordinary precision in almost every measurement we have ever made, are also the theories whose own architects increasingly believe are hiding something fundamental from us. This is not a fringe view. It is, at this moment, the mainstream position. Walk into any major physics department in the world, sit with the cosmologists and the particle physicists and the gravitational theorists. Ask them what they believe about the foundations of their field. The answers, almost without exception, will involve a long list of things that the standard theories cannot account for, cannot predict, cannot calculate, without producing answers that are wrong by enormous factors. The standard theories work beautifully for almost everything we measure. The standard theories also have, embedded within them, a series of admissions that something deeper is missing. Tonight, we're going to walk into 5 of these admissions slowly. Each one is a specific gap in our current best understanding. Each one points towards something that the standard theories cannot reach. Each one has, over the past several decades, become a focus of serious work by some of the most thoughtful physicists alive. Before we get started, sit with what is actually being claimed. The claim is not that physics is wrong. Physics works. The cosmic microwave background measurements match the theoretical predictions to within fractions of a percent. The standard model of particle physics predicts the magnetic moment of the electron to better than 1 part in a trillion. General relativity has been confirmed in every test we have managed to design. From the precession of Mercury's orbit to the detection of gravitational waves from black hole mergers, the theories work. They produce predictions that match observations with extraordinary precision. The claim is that the theories, despite working, are admitting through their own internal structure that something is missing. The cosmic energy budget contains components that we cannot identify. The fundamental forces refuse to unify in any clean way at high energies. The cosmological constant is, by every available calculation, 120 orders of magnitude smaller than the natural prediction. The fundamental constants of nature appear, by every available analysis, to be fine-tuned to extreme precision for no reason any current theory can explain. The information that falls into black holes appears, by the standard analysis, to be permanently lost in a way that quantum mechanics says cannot happen. These are not minor concerns. They are, by the standards of the field, deep structural problems. The physicists who work on them are, in the typical case, doing some of the most careful and serious work in modern science. The problems are not being ignored. They are being worked on with substantial effort. The progress, despite the effort, has been slow. Tonight, we're going to walk through the 5 biggest of these problems one at a time. We will look at what the problem actually is, how it was identified, what attempts have been made to solve it, and what the current state of the work is. By the end of the night, you will have a clearer picture of why so many serious physicists now believe, often quite openly, that the deepest physics we currently have is hiding something fundamental from us, and that the something may not be hidden much longer. The 5 truths are these. The first truth is that the standard cosmological model says 95% of the cosmic energy budget is made of things we cannot identify. 27% is dark matter, an unknown substance that we infer only from its gravitational effects on galaxies and clusters. 68% is dark energy, an even more mysterious component that drives the accelerating expansion of the universe. Together they account for the vast majority of the cosmos. Together they are, after 50 years of dedicated search, still essentially unidentified. The cosmos is mostly made of things we cannot describe. The second truth is that quantum mechanics and general relativity, our 2 most successful theories, contradict each other at the deepest level. Quantum mechanics describes the world of particles, fields, and probability amplitudes. General relativity describes the world of space-time, gravity, and smooth geometric structure. The 2 theories work beautifully in their separate domains. They fail catastrophically when applied to systems where both quantum effects and gravitational effects are important. The energy regime at which the failure becomes severe, called the Planck scale, is far beyond what we can probe directly. But the failure is mathematical, not just experimental. The two theories cannot both be correct. One or both must be replaced by something deeper. The third truth is that the cosmological constant, the parameter in general relativity that drives the accelerating expansion, has a measured value that disagrees with the simplest theoretical prediction by approximately 120 orders of magnitude. The disagreement is so large that it is sometimes called the worst prediction in the history of physics. The standard theory of particle physics predicts a vacuum energy density that should drive cosmic expansion at an enormous rate. The observed cosmic expansion is much slower. The two values differ by a factor that is, in any meaningful sense, beyond comprehension. The problem has been known for decades. No resolution has been agreed upon. The fourth truth is that the fundamental constants of physics appear to be finely tuned to extraordinary precision in ways that no current theory can explain. If the strength of gravity were slightly different, stars could not form. If the strong nuclear force was slightly weaker, atomic nuclei could not be stable. If the cosmological constant was slightly larger, the universe would have expanded too quickly for galaxies to assemble. The list of fine-tuning conditions is long. The combined statistical probability of all the conditions being met by chance, under any reasonable prior, is extraordinarily small. The cosmos appears to be configured for the kind of structures that allow our existence, with no current theory able to explain why. The fifth truth is that black holes appear, by the standard analysis combining general relativity and quantum mechanics, to destroy the information they contain in a way that the laws of quantum mechanics forbid. The contradiction, called the black hole information paradox, was identified by Stephen Hawking in 1974 and has been the subject of intensive theoretical work ever since. The resolution remains contested. The leading candidate resolutions involve the holographic principle, which suggests that the information content of a region of space-time is encoded on its boundary rather than within its volume. The holographic principle, if it is correct, implies that the apparent three-dimensional reality we observe may be a kind of projection from a deeper two-dimensional encoding. 5 truths. 5 admissions that the standard theories, despite their success, are hiding something deep. By the end of tonight, you will have walked slowly through each one, with enough detail to feel the weight of what is being admitted, and enough perspective to see why so many serious physicists now believe the next major theoretical breakthrough is not far away. Pattern interrupt. The tone of this story should not be alarm. Physics is not in crisis in the popular sense. It is in an unusually rich theoretical period, with many deep questions on the table simultaneously, and substantial work being done to address them. What feels from one angle like a confession of ignorance looks from another angle like the natural prelude to a major theoretical advance. Tonight, we will sit with both feelings, the strangeness and the productive excitement, because both are appropriate responses to where physics actually is. Now, let's begin with the first truth, and the first truth requires us to walk carefully through what we mean when we say that 95% of the cosmos is made of things we cannot identify. The first truth came into focus over the course of about a century. The idea that there might be unseen matter in the cosmos goes back to the work of the Swiss astronomer Fritz Zwicky in 1933. Zwicky was studying the motion of galaxies in the Coma cluster, a large cluster of about 1,000 galaxies in the constellation Coma Berenices. He measured the velocities of the individual galaxies as they orbited within the cluster, and calculated from those velocities the total mass that must be present in the cluster to gravitationally bind it. The mass he derived was much larger than the mass implied by the visible light from the cluster. By his estimate, the cluster needed about 400 times more mass than was actually visible. Zwicky proposed that the missing mass must be present in some form that did not emit light. He called it Dunkel Materie, German for dark matter. The proposal was largely ignored at the time. The astronomical community treated Zwicky's calculation as probably affected by some unknown systematic error. The proposal returned to prominence in the 1970s with the work of Vera Rubin and Kent Ford at the Carnegie Institution. Rubin and Ford measured the rotation curves of spiral galaxies, the relationship between the orbital velocity of stars and gas and their distance from the galactic center. The classical expectation, based on the visible distribution of mass, was that the rotation curves should fall off at large distances from the center, with stars at the edge of the galaxy moving more slowly than stars near the center. Rubin and Ford found the opposite. The rotation curves were flat at large distances. Stars at the edge of galaxies were moving at essentially the same speed as stars near the middle. The implication was that there must be substantial unseen mass distributed throughout each galaxy, extending out far beyond the visible boundaries, providing the gravitational pull that kept the outer stars in their high-speed orbits. By the end of tonight, you're going to understand that the Rubin-Ford observations transformed the field. The flat rotation curves were observed in galaxy after galaxy. The pattern was consistent. The implication was inescapable. Galaxies were embedded in much larger halos of unseen matter, with the halos containing several times the total visible mass of the galaxies themselves. Dark matter, dismissed in Zwicky's time, became a central feature of modern cosmology. The cosmic microwave background measurements of the early 2000s and later refined the dark matter picture substantially. The temperature variations in the cosmic microwave background depend sensitively on the total matter content of the universe. The Planck satellite measurements, completed in 2013, established the cosmic dark matter density to high precision. Dark matter accounts for approximately 27% of the total cosmic energy budget. Ordinary matter, the kind that makes up stars, planets, and people, accounts for approximately 5%. The cosmos is mostly made of dark matter by a factor of about 5 to 1. The nature of dark matter has been the subject of intensive theoretical and experimental work for the past 5 decades. The leading candidates are weakly interacting massive particles called WIMPs, which would be heavy particles that interact only weakly with ordinary matter. The Xenon experiment, the Lux-Zeppelin experiment, the Pandex experiment, and various other direct detection experiments have been searching for WIMP interactions with sensitive detectors deep underground, where cosmic ray backgrounds are reduced. The searches have so far produced no confirmed detections. The parameter space for traditional WIMP models has been substantially narrowed by the negative results. Alternative candidates have received increasing attention. Axions, very light particles that were originally proposed to solve an unrelated problem in particle physics, have become one of the leading candidates. The ADMX experiment at the University of Washington has been searching for axions for years and has begun to enter the most promising mass range. Sterile neutrinos, primordial black holes, and various other exotic possibilities have all been proposed. The actual identity of dark matter remains unknown. The picture for dark energy is even more uncertain. Dark energy was discovered in 1998 through observations of distant type Ia supernovae by 2 independent teams. The observations show that the cosmic expansion is accelerating, not decelerating as had been expected. The implication was that some form of energy is driving the acceleration, and the energy must have an equation of state with negative pressure to produce the observed effect. Dark energy accounts for approximately 68% of the total cosmic energy budget. Its nature, in detail, remains unknown. The simplest explanation for dark energy is a cosmological constant, a constant energy density that pervades all of space and drives accelerating expansion. The cosmological constant explanation is consistent with all observations to date, but it raises severe theoretical difficulties that we will explore in the third truth tonight. Alternative explanations for dark energy include time-varying dark energy, modifications to general relativity, and various exotic possibilities. The DESI program, which we have discussed in other contexts, is currently producing data that may distinguish between these possibilities. Tonight, we're going to spend a longer pass on the experimental search for dark matter, because the program is one of the most ambitious and patient experimental efforts in modern physics, and the consistent negative results are an important part of what physics is currently admitting. The systematic experimental search for dark matter began in the 1980s. The basic strategy was to look for rare interactions between dark matter particles and ordinary matter in extremely sensitive detectors. The detectors needed to be shielded from cosmic rays and other backgrounds that would otherwise overwhelm any rare dark matter signal. The shielding was achieved by placing the detectors deep underground, in mines and tunnels that provide kilometers of rock between the detector and the surface. The first generation of underground dark matter experiments included the DARMA collaboration in Italy, the CDMS experiment in Minnesota, and various other smaller programs. The experiments used different detection techniques, including bolometric detection of small temperature increases from particle interactions, ionization detection in semiconductor crystals, and scintillation detection of light produced when particles interact with target materials. Each technique had its own advantages and limitations. By the end of the 1990s, the search had begun to produce its first meaningful upper limits on the dark matter interaction cross-sections. No confirmed detections had been made. The DARMA collaboration claimed an annual modulation signal that they argued was consistent with dark matter interactions, but the signal was not confirmed by other experiments using similar techniques. The DARMA result has remained controversial for decades, with most of the community treating it as probably not a real dark matter signal, but with no definitive explanation for the modulation. Pattern interrupt. The second generation of dark matter experiments, in the 2000s and 2010s, used much larger and more sensitive detectors. The Xenon program conducted at the Gran Sasso laboratory in Italy used large volumes of liquid xenon as the target material. The xenon, being a heavy noble gas, has a high probability of interacting with dark matter particles compared to lighter materials. The Xenon 10, Xenon 100, and Xenon 1 ton experiments progressively increased the detector mass and improved the sensitivity. The LUX experiment at the Sanford Underground Research Facility in South Dakota used similar techniques with a different specific implementation. The Pandux experiment at the Jinping Underground Laboratory in China provided additional independent measurements. All three experiments, by the late 2010s, had reached sensitivity levels that ruled out large portions of the previously favoured dark matter parameter space. By the end of tonight, you're going to understand that the third and current generation of experiments is dramatically larger and more sensitive. The Lux-Zeppelin experiment, sometimes abbreviated LZ, uses approximately 7 metric tons of liquid xenon and is currently operating at the Sanford facility. The Xenon-NT experiment in Italy uses approximately 8 metric tons of liquid xenon. The Pandux 4T experiment uses approximately 4 metric tons of liquid xenon in China. Together, these experiments represent the largest and most sensitive dark matter direct detection program ever conducted. The current sensitivity levels approach what is sometimes called the neutrino floor. The neutrino floor is the level of sensitivity at which the experiments would start detecting neutrinos from the Sun and from cosmic sources at rates comparable to the expected dark matter signal. Beyond this level, distinguishing dark matter from neutrino backgrounds becomes substantially more difficult. The current generation of experiments is approaching this floor, and the next generation will need to develop new techniques to push further. No one expects, on first thinking about dark matter, that the systematic experimental search would have produced essentially complete negative results across multiple decades. No one predicts that the leading dark matter candidates would, by careful experimental work, have been progressively eliminated as parameter space has been explored, absolutely no one anticipates the way the negative results have paradoxically sharpened our understanding of what dark matter probably is not, even in the absence of any confirmed positive detection. The negative results have substantial implications. The original favoured candidates for dark matter, the weakly interacting massive particles called WIMPs, have been pushed into smaller and smaller parameter regions. The simplest WIMP models, with masses around 100 giga-electron-volts and interaction strengths comparable to weak nuclear interactions, have been ruled out by the experiments. The remaining viable parameter space is smaller and more contrived than the original natural expectations allowed. This has shifted the theoretical community toward alternative candidates. Axions, originally proposed in 1977 by Roberto Peccei and Helen Quinn to solve a different problem in particle physics, have become one of the leading alternatives. Axions would be very light particles, with masses possibly in the microelectron-volt range, and they would interact with ordinary matter even more weakly than WIMPs. The ADMX experiment at the University of Washington has been searching for axions for over a decade, and has begun to enter the most promising mass range. Walk with me through the broader implications. The dark matter search has, over 40 years, produced one of the cleanest empirical examples of physics admitting its own incompleteness. The standard cosmological model requires dark matter to exist. The dark matter contributes substantially to the cosmic energy budget. The various direct detection experiments have failed to find it across the most natural parameter ranges. The actual nature of dark matter remains, despite the extraordinary effort, unknown. Hold this image. 40 years of underground experiments, multiple generations of detectors, multiple competing technical approaches, negative results across essentially the entire program. The dark matter problem is, by any reasonable measure, one of the most carefully investigated empirical questions in modern physics, and the careful investigation has produced essentially no answer about what dark matter actually is. The hiddenness is real. The investigation has not yet been able to lift it. By the end of tonight, you're going to understand that this is part of why the search for dark matter has become such a productive area of research, despite the long history of negative results. The negative results are themselves informative. They tell us specifically what dark matter is not. The narrowing of the parameter space pushes the theoretical community toward new candidates and new search strategies. The work continues, with substantial energy and substantial resources, in the expectation that the next generation of experiments may finally produce the long-awaited positive detection. Hold this image. 95% of the cosmic energy budget is made of things we cannot identify. 27% is dark matter, unknown after 50 years of search. 68% is dark energy, even more mysterious. The standard cosmological model that successfully predicts the cosmic microwave background is the same standard cosmological model that requires us to acknowledge that we do not know what most of the cosmos is made of. The success of the predictions and the depth of the ignorance coexist in the same theoretical framework. The second truth is that quantum mechanics and general relativity, the two most successful theories in modern physics, are mathematically incompatible at the deepest level. Tonight, we're going to walk into this slowly, because the incompatibility is one of the most consequential open problems in fundamental physics, and has been the subject of intensive theoretical work for the better part of a century. The two theories were developed in roughly the same period. General relativity was completed by Albert Einstein in 1915. Quantum mechanics, in its modern form, was developed by Heisenberg, Schrödinger, Dirac and others in the mid-1920s. The two theories addressed fundamentally different regimes of physical reality. General relativity described the large-scale structure of space-time, including gravity, the dynamics of the universe, and the behavior of light and matter in strong gravitational fields. Quantum mechanics described the small-scale structure of matter, including atoms, molecules, subatomic particles, and the probability amplitudes that govern their interactions. For most physical situations, the two theories operate in completely separate regimes. The quantum effects on atoms and molecules are described by quantum mechanics without needing general relativity. The gravitational effects on planets, stars, and galaxies are described by general relativity without needing quantum mechanics. The vast majority of physical phenomena fall cleanly into one regime or the other. Pattern interrupt. The problem appears when systems combine both regimes simultaneously. Black holes, the very early universe just after the Big Bang, and certain exotic theoretical scenarios all involve situations where both quantum effects and gravitational effects are important. In these situations, the two theories must somehow be combined. The combination, after a century of theoretical work, has not been achieved in any complete or consistent way. By the end of tonight, you're going to understand that the incompatibility is not just a matter of mathematical inconvenience. It is a deep structural problem. The two theories make different assumptions about the nature of physical reality at the foundational level. Quantum mechanics treats space-time as a fixed background against which quantum systems evolve. General relativity treats space-time as a dynamical quantity that responds to the matter and energy within it. The two pictures, taken at the strictest interpretation, cannot both be true. One or both must be modified to allow them to coexist. The energy regime at which the incompatibility becomes severe is called the Planck scale, named after Max Planck. The Planck scale corresponds to energies of approximately 10 to the 19th giga-electron-volts, which is 15 orders of magnitude beyond the maximum energy currently achievable at the Large Hadron Collider. At Planck scale energies, quantum effects become significant on the same length scales as gravitational effects. The standard formulations of quantum mechanics and general relativity both break down in this regime. The actual physics of the Planck scale must, presumably, be described by some deeper theory that contains both quantum mechanics and general relativity as approximations valid in their respective regimes. The search for this deeper theory has been the central project of fundamental theoretical physics for the past 50 years. The two main approaches are string theory and loop quantum gravity, though several other approaches have been developed. String theory was developed beginning in the late 1960s, with major contributions from John Schwartz, Michael Green, Edward Witten, and many others. The basic idea is that the fundamental constituents of matter are not point particles, but tiny vibrating strings, with the different vibrational modes of the strings corresponding to the different observed particles. String theory naturally incorporates both quantum mechanics and general relativity in a single framework, which is one of its principal attractions. The framework, however, requires extra spatial dimensions beyond the three we observe. The standard version requires 10 space-time dimensions, with the extra dimensions being curled up into compact shapes, too small to observe directly. By the end of tonight, you're going to understand that string theory has been the dominant approach to quantum gravity for several decades, but it has not yet been confirmed by any experimental result. The energy scales required to directly test string theory predictions are beyond the reach of any conceivable accelerator. The theoretical framework has produced many internal results, including the duality relationships between different versions of the theory and the holographic ADAS-CFT correspondence that we will discuss later. But the experimental tests have remained out of reach. Loop quantum gravity, developed beginning in the 1980s by Abhay Ashtekar, Lee Smolin, Carlo Rovelli and others, takes a different approach. Instead of replacing point particles with strings, loop quantum gravity attempts to quantize spacetime itself directly. The theory predicts that spacetime is not smooth at the Planck scale, but is composed of discrete units, with the geometry of space itself being a quantum mechanical structure. Loop quantum gravity does not require extra dimensions, but it has its own technical difficulties, including the challenge of recovering the smooth spacetime of general relativity in the appropriate classical limit, other approaches to quantum gravity have been developed. Causal dynamical triangulations, asymptotic safety, group field theory, and various other programs have each attracted serious work. None of them has been confirmed by experiment. The theoretical landscape remains diverse, with multiple candidate frameworks competing without clear empirical input to decide between them. Walk with me through what this implies for our understanding of physical reality. The incompatibility between quantum mechanics and general relativity is not just an abstract concern. It implies that our current best theories cannot describe certain physical situations. The interior of a black hole, just inside the event horizon, contains regions where both quantum effects and gravitational effects are important. We cannot describe what happens there with our current theories. The earliest moments of the Big Bang, when the cosmos was at Planck scale energies, are similarly beyond the reach of our current frameworks. We cannot describe the actual origin of the cosmos with the theories we have. The deep nature of space-time at the smallest scales is unknown. No one expects, on first hearing about modern physics, that the two most successful theoretical frameworks would be mathematically incompatible at the deepest level. No one predicts that the cosmos contains physical regions that our current theories cannot describe. Absolutely no one anticipates the way the incompatibility has remained unresolved for nearly a century, despite intensive theoretical work by some of the most able minds in modern physics. Pattern interrupt. The implications for the question of what physics is hiding are direct. If quantum mechanics and general relativity are both correct in their respective regimes, then the regime where both apply must be described by some deeper theory that we have not yet discovered. The deeper theory, if it exists, contains information about the structure of physical reality that our current theories do not access. Physical reality has, in this sense, a deeper level that our current best descriptions cannot reach. That deeper level is, by every available indication, what physics is currently hiding from us at the foundational scale. By the end of tonight, you're going to understand that this is one of the most consequential admissions in modern physics. The standard frameworks, despite their success, openly acknowledge their own incompleteness. The Planck scale physics that should connect them remains after a century of work beyond our grasp. The cosmos contains structural features at the smallest scales that we cannot describe. The hiddenness is real, in the strict mathematical sense that no current theory contains the necessary information. Take a moment to sit with this. The cosmos that contains your body, your brain, and your immediate environment is, at the deepest level, governed by physics that our best theories cannot describe. The atoms in your body are quantum mechanical systems. The space between them is a relativistic continuum. The combination of the two, taken at the strictest interpretation, requires a theory we do not yet have. You are alive in a cosmos whose foundational physics is, in this respect, hidden from you and from every physicist who has ever lived. Before we walk into the third truth, take a slow breath here. The story is about to take a brief turn into a different kind of conversation. We should pause to acknowledge why this kind of careful walk through the limits of physics exists at all. Tonight, we're going to walk carefully through the specific theoretical approaches to quantum gravity, because the diversity of attempts and the lack of clear progress is itself one of the more telling features of where physics currently stands. The fundamental difficulty is straightforward in principle and extraordinarily difficult in practice. Quantum mechanics, when applied to gravity using the standard methods that work for the other forces, produces non-renormalizable infinities. The infinities appear in calculations at every order of perturbation theory. The standard techniques for dealing with infinities in quantum field theory, called renormalization, do not work for gravity. The theory, in its naive quantum form, is mathematically inconsistent at the deepest level. This difficulty was identified essentially as soon as physicists began to attempt to quantize gravity in the 1950s and 60s. The various early attempts produced theories that were either internally inconsistent or that produced predictions in clear contradiction with observed physics. The problem was recognized as fundamental rather than merely technical, and the search for a different approach began in earnest in the 1960s. Pattern interrupt. String theory was developed beginning in the late 1960s, initially as a theory of the strong nuclear force. The basic idea was that the fundamental constituents of matter are not point particles, but tiny one-dimensional strings, with the different vibrational modes of the strings corresponding to different observed particles. The framework was abandoned as a theory of the strong nuclear force in the early 1970s, when quantum chromodynamics provided a better description. The framework was revived in the late 1970s and early 80s, when it was discovered that string theory naturally incorporates both quantum mechanics and general relativity in a mathematically consistent way. By the end of tonight, you're going to understand that this incorporation is one of the principal attractions of string theory. The theory does not have the non-renormalizable infinities that plague the naive quantum gravity approach. The interactions of strings at the deepest level produce finite results. The theory automatically contains a particle, the graviton, which is the quantum of the gravitational field. The graviton emerges naturally from the spectrum of string vibrations. The price for this consistency is high. String theory requires extra spatial dimensions beyond the 3 we observe. The standard versions require 10 total spacetime dimensions, including the time dimension, and 9 spatial dimensions. The extra 6 spatial dimensions must be curled up into compact shapes too small to observe directly. The specific compact shape determines the physical constants and laws of the 4-dimensional universe that emerges. The number of possible compact shapes, called the string theory landscape, is enormous, perhaps 10 to the 500th or more. The empirical status of string theory has been controversial. The energy scales at which string theory predictions become substantially different from those of standard quantum field theory are far beyond what any current or proposed particle accelerator can reach. The theory cannot be directly tested at currently accessible energies. The internal mathematical consistency of the theory is well established. The applicability of the theory to our specific cosmos is, however, unconfirmed. Loop quantum gravity, developed beginning in the mid-1980s, takes a fundamentally different approach. Instead of replacing point particles with strings, loop quantum gravity attempts to apply standard quantum techniques directly to the gravitational field, but using a different mathematical formulation than the one that produces the non-renormalizable infinities. The framework was initiated by Abhay Ashtekar in 1986, building on earlier work by Amitabh Sen, and was substantially developed by Lee Smolin, Carlo Rovelli, and others over the following decades. The basic mathematical structure of loop quantum gravity uses what are called Wilson loops, closed loops in space along which the gravitational field is evaluated. The theory treats these loops as the fundamental quantum objects, with the geometry of space itself being a derived quantity. The theory predicts that spacetime is not smooth at the Planck scale, but is composed of discrete quantum units, with the geometry being a kind of quantum spin network. By the end of tonight, you're going to understand that loop quantum gravity has its own technical difficulties. The classical limit of the theory, in which the discrete quantum geometry should reduce to the smooth spacetime of general relativity, has been difficult to establish rigorously. The theory has not yet been shown to reproduce all the predictions of general relativity in the appropriate limit. The framework remains an active area of research, with substantial work being done to address these technical difficulties. Other approaches to quantum gravity have been developed. Causal dynamical triangulations developed by Jan Ambjorn, Renate Loll and others model spacetime as a collection of discrete simplexes that are summed over to produce the path integral of quantum gravity. The approach has produced interesting numerical results, suggesting that the spectral dimension of spacetime may change with scale. Asymptotic safety, developed by Steven Weinberg and others, proposes that gravity may be quantizable, using standard methods if the renormalization group flow has a non-trivial fixed point at high energies. The proposal would resolve the non-renormalizability problem by suggesting that the standard methods produce sensible results in a particular technical limit. Group field theory, causal set theory, twistor theory, and various other approaches each have their own communities of researchers and their own technical content. None of them has been confirmed by experiment. The theoretical landscape for quantum gravity is, in this sense, more diverse than the corresponding landscape for any other fundamental theoretical question in modern physics. No one expects, on first thinking about quantum gravity, that the field would have such a diverse landscape of competing approaches after a century of work. No one predicts that no single approach would have emerged as clearly correct despite the substantial effort. Absolutely no one anticipates the way the lack of empirical input has allowed the theoretical landscape to remain unusually diverse and unresolved. The implications for what physics is hiding are substantial. The actual physics at the Planck scale, whatever it turns out to be, contains information about the fundamental structure of space-time that all current frameworks struggle to access. The different approaches to quantum gravity each provide candidate descriptions of this hidden physics. None of them has been confirmed. The actual Planck scale physics is, in this strict sense, currently hidden from us by both experimental and theoretical limitations. Hold this image: a century of work on quantum gravity. Multiple competing approaches with substantial theoretical development. No clear winner. No direct experimental tests. The Planck scale physics remains, by every available measurement and by every available theoretical framework, beyond our grasp. The hiddenness is one of the most stubborn in modern physics. Whether it will be lifted in the coming decades, or whether it will persist for further generations, is one of the more uncertain questions in contemporary fundamental research. Before we continue, why this channel exists. If you have made it this far into a careful examination of the deepest gaps in modern physics, you are not the casual viewer the platform expects. You are the person for whom this channel was built. Long-form thinking about the foundations of physics, at the pace of sleep, with the technical care that the subject actually requires, rather than the soundbite version that fits a 5-minute summary, is not what the algorithm rewards. It is what we make anyway, because we believe the deepest questions in physics deserve to be developed slowly, rather than collapsed into viral fragments. If that resonates with you, the simplest thing you can do for the channel is to subscribe. Subscribing tells the platform that long, calm, careful work is worth surfacing for the next person who needs a quieter way to think about the limits of human understanding. If you have already subscribed, thank you, truly. If this is your first long-form night with the channel, welcome. The queue contains many more nights like this one. A small additional note. If Spotify is where you find yourself on sleepless nights, consider following the show there. The audio versions are tuned for the same purpose, the same pace, the same care. We want to be a slow companion across both surfaces. Now let us return to the physics. The third truth is waiting. The third truth is one of the most embarrassing results in modern physics. The cosmological constant problem is the disagreement between the theoretical prediction for the vacuum energy of empty space and the observed value driving the accelerating expansion of the cosmos. The disagreement is approximately 120 orders of magnitude. It is sometimes called the worst prediction in the history of physics. Tonight, we're going to walk through this carefully, because the cosmological constant problem is a clear and specific example of how the standard frameworks openly admit that something deep is wrong. Before we get started, sit with what follows. The story begins with quantum field theory, the theoretical framework that underlies the standard model of particle physics. Quantum field theory treats the vacuum, the empty space between particles, as a dynamical entity full of fluctuating quantum fields. Even in the absence of any particles, the quantum fields oscillate continuously, producing a kind of background activity called vacuum fluctuations. The vacuum, in the quantum field theory picture, is not nothing. It is a busy quantum medium with its own energy content. The energy content of the vacuum can be calculated. The calculation involves summing over all the possible modes of all the quantum fields that exist in the standard model. Each mode contributes a small but non-zero amount of energy. The sum, when carried out with standard methods, produces an extraordinarily large result. The natural value of the vacuum energy density, according to quantum field theory, is approximately 10 to the 74th Geiger electron volts per cubic centimeter. The number is so large that, written out in conventional units, it would have 74 zeros after the leading digit. By the end of tonight, you're going to understand why this matters. The vacuum energy contributes to the energy density of the cosmos. In general relativity, any energy density drives the expansion or contraction of space-time, depending on its equation of state. Vacuum energy, with its specific properties, drives accelerating expansion. The rate of acceleration is proportional to the vacuum energy density. If the vacuum energy were as large as quantum field theory predicts, the cosmos would have expanded so rapidly that no galaxies could ever have formed, no stars could ever have ignited, no planets could ever have come into being. The cosmos has, however, formed galaxies, stars, and planets. The observed cosmic expansion is slow. The implied vacuum energy density, derived from the observed expansion rate and from cosmic microwave background measurements, is approximately 10 to the minus 46 giga-electron volts per cubic centimeter. The number is, in any meaningful sense, very small. Pattern interrupt. Compare the two values. The theoretical prediction from quantum field theory is approximately 10 to the 74th giga-electron volts per cubic centimeter. The observed value is approximately 10 to the minus 46 giga-electron volts per cubic centimeter. The ratio between the two is approximately 10 to the 120th. Written out in conventional notation, this is a 1 followed by 120 zeros. The theoretical prediction exceeds the observed value by a factor that is, in any practical sense, beyond comprehension. This is the cosmological constant problem. The standard theoretical framework predicts a value for vacuum energy that is wrong by one of the largest factors ever computed in physics. The framework is, despite the error, the best available description of vacuum energy. The error is, despite its magnitude, the most precise theoretical prediction we have for this quantity. The problem has been known, in its modern form, since the late 1960s. The astronomer Yakov Zeldovich wrote one of the first papers explicitly identifying the issue in 1968. Steven Weinberg published the most influential analysis of the problem in 1989. The problem has, in the decades since, become one of the most studied open problems in fundamental physics. It has, despite the intensive work, not been resolved. By the end of tonight, you're going to understand the various attempts to resolve the cosmological constant problem. They fall into several broad categories. The first category of resolution involves invoking some symmetry or principle that forces the vacuum energy to cancel to extraordinary precision. The idea is that the various contributions to the vacuum energy, while each individually very large, sum to a much smaller value because of some underlying constraint. Supersymmetry was originally proposed partly because it produces such cancellations. The various fermion and boson contributions to vacuum energy, in a supersymmetric theory, would cancel against each other. The cosmological constant, in a perfectly supersymmetric world, would naturally be zero. The problem with the supersymmetry resolution is that we do not appear to live in a perfectly supersymmetric world. The supersymmetric partners of the standard model particles, if they exist, must be substantially heavier than the standard model particles themselves. The cancellations from broken supersymmetry are imperfect. The residual vacuum energy, even with supersymmetry, would still be much larger than the observed value. Supersymmetry, despite being a natural candidate, does not by itself resolve the problem. The second category of resolution involves anthropic reasoning. The idea is that the cosmological constant is a free parameter that can take different values in different regions of the universe, with the value we observe being selected by the fact that we exist as observers. In regions where the cosmological constant is very large, no observers can exist because no structure can form. In regions where the cosmological constant is small enough, observers can exist and they observe a small cosmological constant. The argument was made most influentially by Steven Weinberg in 1987, who predicted the order of magnitude of the cosmological constant before it was measured, using anthropic reasoning. The anthropic resolution has been controversial. Some physicists find it deeply unsatisfying, arguing that anthropic reasoning is not a real explanation, but rather an admission that we cannot calculate the value from first principles. Others find it compelling, particularly in the context of the string theory landscape, where many possible vacuum states exist, and the anthropic selection naturally picks out the ones compatible with observers. The debate has been productive but has not produced consensus. The third category of resolution involves modifying gravity itself at large scales. If general relativity is not quite the correct description of gravity over cosmic distances, then the relationship between vacuum energy and cosmic acceleration might be different from what the standard analysis predicts. Various modified gravity theories have been proposed. None has been shown to be definitively correct. The DESI program, which we have discussed, is currently producing data that may constrain these alternatives. No one expects, on first encountering the cosmological constant problem, that one of the most precise theoretical predictions in modern physics could be wrong by 120 orders of magnitude. No one predicts that the standard framework would openly admit such a large quantitative discrepancy. Absolutely no one anticipates the way the problem has remained unresolved for nearly 70 years, despite the work of many of the most able physicists alive. Walk with me through what this implies for the question of what physics is hiding. The cosmological constant problem is a clear and specific case in which the standard framework produces a quantitative prediction that disagrees with observation by an enormous factor. The framework is, despite the discrepancy, the best available description of vacuum energy. The discrepancy is, despite its magnitude, embedded within the very structure of the theory. The implication is that the standard framework is missing some essential feature of vacuum energy. The framework is treating vacuum fluctuations in a way that produces a prediction that nature appears to violate. The actual physics of vacuum energy, whatever it turns out to be, must include some mechanism that suppresses the natural prediction to the observed value. That mechanism is, by every available indication, currently hidden from us. We do not know what it is. We have not been able to find it through any direct calculation. Tonight we're going to walk carefully through the specific calculation that produces the cosmological constant problem, because understanding the calculation in some detail helps clarify why the discrepancy is so disturbing and why it has resisted resolution. The calculation begins with the vacuum state of quantum field theory. In quantum field theory, every type of fundamental field has a vacuum state, which is the state with the lowest possible energy. The vacuum is not, in general, a state with zero energy. The Heisenberg uncertainty principle requires that quantum fields have non-zero fluctuations even in the vacuum state, and these fluctuations contribute energy to the vacuum. The specific energy contribution of each field can be calculated by summing all possible modes of the field. Each mode is associated with a particular frequency, and each mode contributes a zero-point energy proportional to half its frequency. The total vacuum energy is the sum of all these zero-point energies integrated over all possible frequencies up to some cutoff scale. By the end of tonight, you're going to understand why the choice of cutoff matters. The integral over all possible frequencies diverges at high frequencies. To produce a finite answer, the calculation must be cut off at some maximum frequency. The natural choice for the cutoff in a quantum gravity context is the Planck frequency, the frequency corresponding to the Planck energy. The Planck frequency is approximately 10 to the 43 Hz, which is an extraordinarily high frequency by any ordinary standard. when the integral is performed with the Planck cutoff, the resulting vacuum energy density is approximately 10 to the 74th giga-electron-volts per cubic centimetre. This is sometimes referred to as the natural value of the vacuum energy from quantum field theory considerations. Pattern interrupt. Compare this to the value of the vacuum energy that drives the observed cosmic acceleration. The cosmological constant in general relativity is related to the vacuum energy by a specific equation. The observed cosmic expansion rate, combined with the cosmic microwave background measurements and various other cosmological observations, implies a cosmological constant whose energy equivalent is approximately 10 to the minus 46 giga-electron-volts per cubic centimetre. The ratio between the calculated value and the observed value is approximately 10 to the 120th. The disagreement is not subtle. It is, in any meaningful technical sense, the worst quantitative prediction in the history of theoretical physics. Other discrepancies between theory and observation have been at the few percent level, the few sigma level, occasionally at orders of magnitude. The cosmological constant problem is a discrepancy of 120 orders of magnitude, which is in a category of its own. Various proposals have been made to address the calculation itself. One possibility is that the proper cutoff is not the Planck scale but some lower scale, perhaps the electroweak scale or some other scale set by physics beyond the standard model. If the cutoff were the electroweak scale, the vacuum energy from quantum field theory would still be approximately 10 to the 8th giga-electron-volts per cubic centimetre, which is still substantially larger than the observed value, but the discrepancy would be approximately 50 orders of magnitude rather than 120. Another possibility is that some symmetry forces the vacuum energy to cancel between different contributions. The standard candidate for such a symmetry is supersymmetry, which we discussed in another context. In a perfectly supersymmetric theory, the contributions from fermion fields and boson fields cancel against each other exactly, producing zero vacuum energy. The observed cosmos, however, is not perfectly supersymmetric. If supersymmetry exists at all, it must be broken at some scale. The amount of residual vacuum energy from broken supersymmetry depends on the supersymmetry breaking scale. Even with the most optimistic assumptions, the residual vacuum energy is still substantially larger than the observed value. A third possibility is that the actual cosmological constant is a sum of two large numbers that nearly cancel. The natural quantum field theory contribution is positive and very large. Some other contribution, perhaps from the deep structure of quantum gravity, is negative and almost exactly the same magnitude. The sum is the small observed value. The problem with this proposal is that the cancellation must be accurate to 120 decimal places, which seems extraordinarily implausible without some underlying reason for the cancellation. No one predicts, on first thinking about quantum field theory, that the calculation of vacuum energy would produce one of the most embarrassing discrepancies in physics. No one expects that the cancellation between theoretical prediction and observed value would need to be so precise that no plausible mechanism can produce it. Absolutely no one anticipates the way the cosmological constant problem has, despite the intensive theoretical effort, resisted all proposed resolutions for nearly 70 years. The most influential modern response to the problem invokes anthropic reasoning combined with the multiverse, as we discussed in the main text. The argument is that the cosmological constant takes different values in different regions of the cosmos, with the value we observe being selected by the requirement that observers exist. The argument was made most influentially by Steven Weinberg in 1987, who used anthropic reasoning to predict the order of magnitude of the cosmological constant before it was experimentally measured. Weinberg's prediction was remarkably close to the value that was eventually measured a decade later. The anthropic response has been controversial. Some physicists find it unsatisfying because it shifts the explanation from physics to selection bias. Others find it compelling because it provides a quantitative prediction that matches observation. The argument continues to be debated. with the broader question of whether anthropic reasoning constitutes a legitimate form of scientific explanation being one of the more contested issues in modern theoretical physics. Notice that the cosmological constant problem is, in a sense, the clearest single example of the broader theme we have been walking through. The standard frameworks produce specific quantitative predictions. The cosmos provides specific quantitative observations. The two disagree by enormous factors. The standard frameworks are, despite the disagreement, the best available descriptions. The disagreement is acknowledged. The resolution remains contested. The hiddenness is precise and stubborn. Hold this image. The simplest calculation in quantum field theory, applied to the cosmological constant problem, produces a prediction that exceeds the observed value by 10 to the 120th. The exceedance is not a subtle effect. It is the worst quantitative prediction in modern physics. The standard frameworks continue to be used because they are the best available. The deeper physics that resolves the discrepancy is, in the strictest sense, hidden from us in the gap between what the theory predicts and what the cosmos actually does. Hold this image. The cosmological constant problem is the cleanest single example of how the standard framework openly admits its own incompleteness. The framework predicts one value, the cosmos shows another. The two values differ by a factor that is beyond ordinary comprehension. The framework continues to be used because it is the best available, but the discrepancy is acknowledged by essentially every working theoretical physicist. The hiddenness in this case is mathematical. The actual physics of vacuum energy is hidden in the gap between what the theory predicts and what the cosmos shows. What this means is that this is part of why so many physicists now believe physics is on the verge of a major theoretical advance. The standard framework has produced specific quantitative admissions of incompleteness. The cosmological constant problem is one of the cleanest. The actual resolution, when it comes, will involve substantial new theoretical structure. The new structure, whatever it turns out to be, will tell us something specific about what the standard framework has been missing for decades. The hidden physics will eventually become visible. The fourth truth concerns the apparent fine-tuning of the fundamental constants of physics, the constants that govern the strengths of the fundamental forces, the masses of the elementary particles, and the structure of the cosmic expansion appear to be configured to extraordinary precision in ways that no current theory can explain. The configuration produces, by all available analysis, a cosmos that permits the existence of complex structure and eventually observers. The configuration also produces, by all available analysis, a cosmos whose parameters are unnatural in the strict technical sense that the standard frameworks cannot derive them. Tonight we're going to walk into this carefully, because the fine-tuning problem has been a central preoccupation of theoretical physics for several decades, and has produced some of the most interesting recent work in the field. The basic situation is this. The standard model of particle physics contains approximately 25 free parameters, including the masses of the various quarks and leptons, the strengths of the gauge couplings, the parameters of the Higgs mechanism, and various mixing angles between different flavors of particles. The values of these parameters are not predicted by the standard model. They are measured experimentally and then inserted into the theory as input. The standard framework treats these parameters as essentially arbitrary. Different values would produce different physical predictions. The actual values, the ones we measure, are whatever they happen to be. The framework does not require any particular values for the parameters. It simply uses whichever values experiment provides. The takeaway is that this becomes problematic when we examine what would happen if the parameters had different values. The analysis has been carried out in considerable detail over the past several decades by physicists including Bernard Carr, Martin Rees, John Barrow, and Frank Tipler. The results are striking. If the strength of the strong nuclear force was slightly weaker, by approximately 10%, the diproton-bound state would be stable, and stars would burn through their fuel in a few seconds rather than billions of years. If the strong nuclear force was slightly stronger, again by approximately 10%, all the hydrogen in the early universe would have fused into helium, and no hydrogen would remain to power long-lived stars. Either modification would prevent the formation of the long-lived stars that allow planetary systems and biological complexity to develop. Pattern interrupt. The list of fine-tuning conditions is long. The mass ratio between the up quark and the down quark, which determines the stability of the neutron, must be within a narrow range. The cosmological constant, as we discussed in the third truth, must be small to allow structure formation. The electromagnetic coupling strength must be in a narrow range to allow stable atoms and stable chemistry. The ratio of the strengths of gravity to the electromagnetic force must be enormously small to allow stars to last for billions of years. The cosmic baryon asymmetry must be approximately 1 part in a billion to leave enough matter for galaxies after early matter-antimatter annihilation. Each of these conditions, taken individually, might be considered a coincidence. The combination of all of them, with the precision that each one requires, is more difficult to dismiss as coincidence. By any reasonable measure, the cosmos appears to be configured for the kind of structure that allows observers to exist. The configuration has, in the technical literature, become known as the fine-tuning problem, or, in some formulations, the multiverse problem. The standard physics framework provides no derivation of the observed parameter values. The parameters are inputs to the theory, not outputs. The framework cannot explain why the strong nuclear force has the strength it does, why the cosmological constant has the value it does, why the electron has the mass it does. The values are what they are. What this picture tells us is that the major proposed responses to the fine-tuning problem. They fall into several categories. The first category involves accepting the fine-tuning as evidence for some deeper organizing principle. If the parameters are not arbitrary, but are determined by some underlying theoretical structure, then the apparent fine-tuning might be a natural consequence of that structure. The search for such a deeper theory has motivated much of the work in fundamental physics over the past several decades. String theory, grand unified theories, and various other approaches all attempt in their different ways to derive the standard model parameters from deeper principles. None has yet succeeded. The second category involves invoking the multiverse. If many universes exist with different parameter values, then the question of why we observe the specific values we do is answered by anthropic reasoning. We exist in the kind of universe whose parameters allow observers to exist. Universes with different parameter values may exist elsewhere in the multiverse, but they do not contain observers like us to wonder about their parameters. The multiverse resolution has been most prominently developed in the context of the string theory landscape, which we discussed in another context. The third category involves modifying the assumption that the parameters need to be fine-tuned. Some researchers have argued that the apparent fine-tuning is an artifact of the specific assumptions we make about what configurations would allow life. Other configurations with different parameter values might also allow some form of life or complex structure that we have not adequately considered. The argument is interesting but has not been fully developed. No one predicts, on first encountering particle physics, that the values of the fundamental constants would appear so precisely tuned for the existence of observers. No one expects that the question of why the constants have the values they do would become one of the deepest open problems in modern theoretical physics. Absolutely no one anticipates the way the fine-tuning analysis would push some physicists toward multiverse hypotheses and others toward deeper unified theories. Now, let's begin to walk through one specific case of fine-tuning that connects to the cosmic origin. The matter-antimatter asymmetry of the early universe is one of the more concrete fine-tuning puzzles. The basic story is this. In the very early universe, just after the Big Bang, matter and antimatter were produced in roughly equal amounts. By the standard physics, matter and antimatter should have annihilated each other almost completely, leaving the cosmos filled only with photons and neutrinos. The actual cosmos contains substantial amounts of matter and very little antimatter. Some small excess of matter over antimatter must have existed in the early universe, allowing some matter to survive the early annihilation. The required excess is approximately 1 part in a billion. For every billion antimatter particles produced, 1,000,000,001 matter particles must have been produced. The conditions required for such an asymmetry to be generated were identified by Andrei Sakharov in 1967. The Sakharov conditions specify 3 requirements. The first is that some physical process must produce a difference in the rates of matter production and antimatter production. The second is that the cosmos must have been out of thermal equilibrium during the process, otherwise the asymmetry would have washed out. The third is that the charge conjugation symmetry must have been violated, otherwise the rates would still match. The standard model contains processes that satisfy all 3 Sakharov conditions in principle. The actual matter-antimatter asymmetry generated by these processes, however, is far too small to match the observed value. Standard model baryogenesis predicts an asymmetry many orders of magnitude smaller than what is actually observed. The standard framework therefore admits that it cannot account for the existence of substantial matter in the cosmos. Pattern interrupt. This is a striking admission. The cosmos contains matter. The matter is, by every available measurement, the matter that makes up everything we can see, including your body. The standard framework cannot explain why the matter is there. Whatever process actually produced the matter-antimatter asymmetry of the early universe must, by every available analysis, involve physics beyond the standard model. The candidate mechanisms for explaining the baryon asymmetry include grand unified theory baryogenesis, leptogenesis through right-handed neutrinos, and electroweak baryogenesis in extensions of the standard model. Each of these mechanisms requires physics beyond the standard model. None has been confirmed experimentally. The actual origin of the matter in the cosmos remains, in this strict sense, unknown. What follows from this is that this is one of the more personal admissions in modern physics. The matter that makes up your body is, by every available indication, the product of some process in the early universe that the standard framework cannot describe. The physics that produced you is, in this sense, hidden in physics beyond the standard model. The hidden physics is real. The standard framework openly admits that it is missing the relevant mechanism. Tonight we're going to spend a longer pass on the matter-antimatter asymmetry problem, because the technical content of the Sakharov conditions and the current candidate mechanisms is one of the more concrete examples of how the standard frameworks openly admit their own incompleteness. The basic observation is straightforward. The cosmos contains substantial amounts of ordinary matter and very little antimatter. The matter forms stars, planets, and biological organisms. The antimatter exists only in trace amounts, produced by high-energy processes such as cosmic rays and certain types of stellar activity. The asymmetry is, by every reasonable measure, large and consistent across all the parts of the cosmos we can observe. This asymmetry is not what would be expected from the standard physics of the early universe. In the very hot, very dense conditions of the early universe, matter and antimatter would have been produced in equal amounts by the standard processes. The standard physics treats matter and antimatter as essentially symmetric. Whatever produces matter also produces antimatter in approximately equal quantities. Any imbalance must come from some specific asymmetric process. Step back, and you can see that the conditions for such an asymmetric process to operate were identified by Andrei Sakharov in 1967. Sakharov was a Soviet physicist who, in addition to his work on fundamental theoretical questions, was deeply involved in nuclear weapons development and later in human rights advocacy. His 1967 paper, published in the journal Letters of the Soviet Academy of Sciences, identified 3 necessary conditions for any process to generate a matter-antimatter asymmetry from an initially symmetric state. The first Sakharov condition, is that the process must violate baryon number conservation. Baryon number is a quantum number that distinguishes between particles like protons and neutrons, which carry positive baryon number, and antiparticles like antiprotons and antineutrons, which carry negative baryon number. A process that conserves baryon number cannot, by definition, change the net baryon number of the universe. Some process must violate the conservation to produce the observed excess of matter over antimatter. The second Sakharov condition is that the cosmos must have been out of thermal equilibrium during the asymmetric process. In thermal equilibrium, the rates of forward and reverse reactions are equal, and any asymmetry produced by one process is undone by the reverse process. Out of thermal equilibrium, the rates can differ, allowing a net asymmetry to develop. In the early universe, periods of substantial deviation from thermal equilibrium occurred during rapid changes in conditions, such as during phase transitions. The third Sakharov condition is that the process must violate the combination of charge conjugation symmetry and parity symmetry, sometimes called CP symmetry. Charge conjugation symmetry interchanges particles with their antiparticles. Parity symmetry reflects spatial directions. If both symmetries are exactly conserved, then any process that produces an excess of matter in one direction would produce an exactly compensating excess of antimatter in the opposite direction, with no net asymmetry. CP violation allows a net asymmetry to develop. Pattern interrupt. The standard model of particle physics contains processes that satisfy all three Sakharov conditions in principle. Baryon number violation occurs through certain rare quantum processes called sphalerons, which are predicted by the electroweak theory. Departures from thermal equilibrium occur during the electroweak phase transition, when the universe cooled through approximately 100 giga-electron volts. CP violation is observed in the weak interactions, particularly in the decays of certain types of mesons. The problem is that the actual amount of asymmetry generated by the standard model processes is far too small to explain the observed baryon asymmetry. The CP violation in the standard model is too weak. The electroweak phase transition is too smooth to produce the necessary departure from thermal equilibrium. The sphaleron processes operate at temperatures and rates that are not optimal for asymmetry generation. The combined effect produces a baryon asymmetry that is, by every available calculation, many orders of magnitude smaller than the observed value. What emerges from this is that this is one of the cleanest cases in which the standard framework openly admits its inability to explain a fundamental observed feature of the cosmos. The observed baryon asymmetry exists. The standard framework cannot produce it. Some physics beyond the standard model must be responsible. The candidus mechanisms for explaining the observed baryon asymmetry fall into several categories. The first category is grand unified theory baryogenesis. In grand unified theories, which attempt to unify the strong, weak, and electromagnetic interactions at very high energies, there are heavy gauge bosons whose decays can violate baryon number. The decays in the very early universe, when the cosmos was at the relevant energy scales, could have produced a baryon asymmetry. The problem with this mechanism is that any asymmetry produced at grand unified energies tends to be washed out by subsequent sphaleron processes. The second category is leptogenesis through right-handed neutrinos. The standard model contains left-handed neutrinos, but does not include their right-handed counterparts. Some extensions of the standard model include right-handed neutrinos with very large masses. The decays of these heavy neutrinos in the early universe could have produced a lepton asymmetry, which would then be partially converted to a baryon asymmetry through sphaleron processes. Leptogenesis is one of the leading candidate mechanisms and has substantial theoretical development. The third category is electroweak baryogenesis, in extensions of the standard model. The standard model electroweak phase transition is too smooth to produce substantial asymmetry. but extended versions of the standard model with additional Higgs sectors or other modifications can produce a sharper phase transition with stronger departure from thermal equilibrium. Combined with stronger CP violation from new sources, the modified electroweak baryogenesis could potentially explain the observed asymmetry. No one expects, on first thinking about cosmic composition, that the question of why there is any matter at all would turn out to require physics beyond the standard model. No one predicts that the fundamental framework would, despite its successes, be unable to explain the existence of the substance that makes up everything we can see. Absolutely no one anticipates the way the matter asymmetry problem connects so directly to the broader picture of physics beyond the standard model. Walk with me through what this implies for the broader theme. The matter that makes up your body, the atoms in your cells, the molecules in your organs, exist because some asymmetric process in the very early universe produced an excess of matter over antimatter. The process that produced this excess is not described by any framework that has been experimentally verified. The candidate mechanisms all involve physics beyond the standard model. The actual mechanism remains unknown. The implication is direct. The substance that constitutes you is, by every available indication, the product of physics that we cannot fully describe. The hidden physics, in this case, is the physics that produced the asymmetry that allowed any matter to exist in the cosmos. Without that hidden physics, you would not exist. The very fact of your existence is, in this sense, a reminder of what the standard framework cannot reach. Hold this thought. The matter-antimatter asymmetry is one of the most concrete examples of how physics openly admits incompleteness. The asymmetry exists. The framework cannot produce it. Some physics beyond the framework must be responsible. No one expects this set of mysteries to be resolvable through any single experiment. The candidate mechanisms have not been experimentally confirmed. The actual physics that produce the matter in the cosmos, including the matter that makes up your body, remains hidden from our current best descriptions. Hold this thought. The fourth truth combines the fine-tuning of the fundamental constants with the matter-antimatter asymmetry to produce a single broad observation. The cosmos that contains you is configured by every available analysis in ways that the standard framework cannot derive. The specific values of the fundamental constants are inputs to the theory rather than outputs. The amount of matter is more than the framework can explain. The cosmos, considered as a particular configuration, sits substantially outside what the standard framework alone would predict. The implication is that the standard framework is missing something fundamental about why the cosmos is configured the way it is. The hidden physics, in this case, includes the principle or mechanism that selects the specific values of the fundamental constants, the mechanism that produced the matter-antimatter asymmetry, and possibly the deeper structure that makes the various parameters appear so precisely coordinated for the existence of complex structure. The standard framework, despite all its successes, cannot reach any of these. The fifth truth is, in some ways, the deepest of all. It suggests that the three-dimensional reality you appear to inhabit may, in some technical sense, be a projection from a two-dimensional encoding on a distant boundary. The hypothesis is called the holographic principle, and it has emerged from work on the black hole information paradox over the past several decades. Tonight, we're going to walk into this carefully, because the holographic principle is one of the most striking theoretical developments in modern physics, and the implications for the nature of physical reality are substantial. The story begins with Stephen Hawking in 1974. Hawking was investigating the quantum mechanical behavior of black holes. He demonstrated, through a careful calculation involving quantum field theory and curved space-time, that black holes are not actually completely black. They emit thermal radiation, now called Hawking radiation, from their event horizons. The radiation has a specific temperature that depends on the mass of the black hole, with smaller black holes being hotter and larger black holes being colder. The implication, when worked out carefully, was disturbing. Hawking radiation causes black holes to lose mass over time. Sufficiently small black holes evaporate completely. The matter that originally formed the black hole and any subsequent matter that fell into it has, by the time the black hole is fully evaporated, been converted into thermal radiation. The thermal radiation, by every available analysis, contains no information about the specific matter that fell in. The information that was originally encoded in the matter appears to be lost when the black hole evaporates. Pattern interrupt. This is the black hole information paradox. The loss of information violates one of the most fundamental principles of quantum mechanics. Quantum mechanics, in its standard formulation, requires that information be conserved in any unitary evolution. The wave function evolves according to the Schrödinger equation, with no loss of the information encoded within it. The evaporation of a black hole into thermal radiation, however, appears to produce a final state that contains less information than the initial state. The contradiction is severe. The point worth taking away is that the information paradox has been the subject of intensive theoretical work for 50 years. Hawking himself originally argued that quantum mechanics must be modified to allow for information loss in the presence of black holes. Other physicists, including Leonard Susskind, John Preskill, and Gerard 't Hooft, argued that quantum mechanics must be preserved and that the information must somehow escape with the Hawking radiation. The debate continued for decades. In 2004, Hawking publicly conceded that the information is probably preserved, though the specific mechanism remained unclear. The leading candidate mechanism for preserving information involves the holographic principle, developed primarily by Susskind and 't Hooft in the early 1990s. The principle states that the information content of a region of space-time is encoded not in the volume of the region but on its boundary. The area of the boundary, measured in Planck units, is sufficient to encode all the information that the region contains. The interior of the region, in this picture, is in some sense redundant. The boundary information is the primary information. The interior is a derived structure. The holographic principle has its most precise formulation in the ADS-CFT correspondence, developed by Juan Maldacena in 1997. ADS-CFT, short for anti-de Sitter/conformal field theory correspondence, establishes an exact mathematical equivalence between certain quantum field theories defined on a lower dimensional space and certain string theories defined on a higher dimensional space. The correspondence has been extensively tested through detailed calculations, with the two sides reproducing each other's predictions to extraordinary precision. Walk with me through what this implies for the question of physical reality. The ADS-CFT correspondence is a precise mathematical statement of the holographic principle in a specific theoretical setting. It says that the entire physical content of a particular kind of universe, with all its three-dimensional structure and dynamics, can be exactly reproduced by a quantum field theory living on the two-dimensional boundary of that universe. The two descriptions are completely equivalent. Either one captures the full physical content. The volume description is not more fundamental than the boundary description. What this leaves us with is that the broader implications, if the holographic principle is correct in our actual universe, then the apparent three-dimensional structure of space may be a derived feature of a more fundamental two-dimensional encoding. The cosmos you experience, with its solid objects and its three-dimensional geometry, may be a kind of projection from information encoded on some distant boundary surface. The boundary may be the cosmic horizon, or the event horizon of black holes, or some more abstract mathematical structure. The specific identification depends on details of the holographic framework that are still being worked out. The empirical status of the holographic principle is mixed. In its specific ADS-CFT form, the principle has been extensively verified through theoretical calculations that show the precise equivalence of the two descriptions. The framework has been used to study problems in nuclear physics, condensed matter physics, and gravitational physics. The theoretical content of the framework is well established. The application to our actual universe is less certain. Our cosmos is not anti-de Sitter space. The cosmos has a positive cosmological constant, corresponding to de Sitter rather than anti-de Sitter geometry. The straightforward add-CFT correspondence does not directly apply. Various attempts have been made to develop a holographic correspondence appropriate for de Sitter space, but none has reached the same level of precision and verification as the ADS case. The application of the holographic principle to our specific cosmos is, in this sense, more conjectural than its application in the ADS setting. No one expects, on first thinking about black holes, that the resolution of the information paradox would lead to a fundamental reconsideration of the nature of physical reality. No one predicts that the apparent three-dimensional structure of the cosmos might, in some technical sense, be derived from a more fundamental two-dimensional encoding. Absolutely no one anticipates the way the holographic principle has, despite the lack of direct experimental confirmation, become one of the most influential theoretical frameworks in modern fundamental physics. The implications for the question of what physics is hiding are substantial. The holographic principle, if correct, implies that the standard three-dimensional description of physical reality is incomplete. The actual fundamental physics is encoded on a lower dimensional boundary. The three-dimensional structure we observe is a derived consequence of the boundary encoding. We do not have direct access to the boundary in the same way we have access to the three-dimensional volume. The boundary is, in this strict sense, the hidden level of physical reality. Hold this image. The cosmos you live in may, in the holographic picture, be a kind of projection. The actual fundamental description of physical reality may exist on some boundary that we cannot directly access. The three-dimensional space, the solid objects, the apparent geometric structure, may all be features of a more fundamental two-dimensional encoding that we do not directly see. The hiddenness, in this case, is not just about specific parameters or specific particles. It is about the dimensional structure of physical reality itself. What becomes clear is that this is perhaps the most far-reaching of the five truths. The first four truths suggest that the standard frameworks are missing specific features of physical reality, including the identity of dark matter and dark energy, the connection between quantum mechanics and gravity, the explanation of the cosmological constant, and the origin of the fine-tuned parameters. The fifth truth suggests something more sweeping. The very dimensionality of physical reality may be a derived feature rather than a fundamental one. The cosmos may have a deeper structure that operates in fewer dimensions than the cosmos we observe. The implications, if the holographic principle is correct, are striking. Your body, your brain, the room you're in, the planet you're on, the cosmos around you, may all be features of a kind of cosmic hologram. The actual fundamental information is encoded somewhere else, on a boundary or surface that we do not directly see. The three-dimensional experience you are having is the projection. The two-dimensional encoding is the more fundamental description. This is, by every available measure, a strange conclusion. It is also taken seriously by significant fractions of the theoretical physics community. The ADS-CFT correspondence is mathematically precise. The black hole information paradox demands some resolution that preserves quantum mechanics. The holographic principle is one of the leading candidates for that resolution. The principle has substantial theoretical support, despite the lack of direct experimental confirmation in our specific cosmos. Tonight we're going to spend a longer pass on the specific history of the black hole information paradox and the development of the holographic principle, because the story is one of the most interesting in modern theoretical physics, and the implications are still being worked out. The story begins with the development of black hole thermodynamics in the early 1970s. Several physicists, including Jacob Bekenstein, Stephen Hawking, and Brandon Carter, recognize that black holes have thermodynamic properties analogous to ordinary thermodynamic systems. Black holes have a temperature, an entropy, and obey laws analogous to the four laws of thermodynamics. The analogy was initially considered a curiosity, but it turned out to be deeply substantive. Bekenstein proposed in 1973 that the entropy of a black hole is proportional to the area of its event horizon, not to its volume. The proposal was unusual because for ordinary thermodynamic systems, the entropy is extensive, meaning it scales with the volume of the system. For black holes, Bekenstein argued, the entropy is proportional to the surface area instead. The specific coefficient of proportionality was the quarter of the area in Planck units. Hawking initially disagreed with Bekenstein, but, in 1974, performed a careful calculation showing that black holes do indeed have a temperature and emit thermal radiation. The Hawking calculation derived the temperature from quantum field theory in the curved space-time of a black hole. The temperature was inversely proportional to the mass of the black hole. The corresponding entropy, derived from the temperature using standard thermodynamic relations, was exactly the area proportional entropy that Bekenstein had proposed. Pattern interrupt. The Hawking calculation was a landmark result. It established that quantum effects modify the classical behavior of black holes in important ways. The thermal radiation, called Hawking radiation, causes black holes to lose mass over time. Sufficiently small black holes evaporate completely over a finite time. The thermal spectrum of the radiation contains, by the standard calculation, no information about the specific matter that originally formed the black hole or fell into it later. The implication was disturbing. Information that was originally encoded in matter, with all its complexity and specificity, appeared to be lost when the matter fell into a black hole, and the black hole subsequently evaporated. The thermal radiation carried away only the bulk thermodynamic properties of the original matter, not the detailed quantum information. The information was, by the standard calculation, gone. What surfaces from this is that this was a profound problem. Quantum mechanics, in its standard formulation, requires that information be conserved in any unitary evolution. The wave function of a closed quantum system evolves according to the Schrödinger equation, with no loss of the information contained within it. The evaporation of a black hole taken at face value appears to produce a final state in which information has been lost. The two principles, conservation of information and the apparent loss of information in black hole evaporation, cannot both be true. The black hole information paradox was thus formulated. Hawking himself originally argued that quantum mechanics must be modified to allow for information loss in the presence of black holes. Other physicists, including Don Page, Leonard Susskind, John Preskill, and Gerard 't Hooft, argued that quantum mechanics must be preserved and that the information must somehow escape with the Hawking radiation. The debate continued for decades, with various positions being defended at length without consensus emerging. A famous bet was made in 1997 between Hawking, Kip Thorne, and Preskill. Hawking and Thorne bet that information is lost in black hole evaporation. Preskill bet that information is preserved. In 2004, Hawking publicly conceded the bet and presented Preskill with the encyclopedia of his choice. Hawking argued that information is probably preserved through some mechanism in the quantum gravitational physics of black hole evaporation, though the specific mechanism remained unclear at the time. The leading candidate mechanism for preserving information involves the holographic principle. The principle was developed primarily by Gerard 't Hooft and Leonard Susskind in the early 1990s. 't Hooft introduced the basic idea in a 1993 paper. Susskind developed it further in a 1995 paper. The principle states that the information content of a region of space-time is encoded not in the volume of the region, but on its boundary, with the area of the boundary providing the upper bound on the total information. Notice that the holographic principle has its most precise formulation in the AD-CFT correspondence, developed by Juan Maldacena in 1997. AD-CFT establishes an exact equivalence between certain string theories defined on anti-de Sitter space, a particular kind of higher dimensional space-time, and certain quantum field theories defined on the boundary of that space. The correspondence has been verified through extensive theoretical calculations, with the two sides reproducing each other's predictions to high precision. The implications of AD-CFT for the black hole information paradox are direct. In the AD-CFT framework, a black hole on the gravitational side corresponds to a particular thermal state on the boundary field theory side. The evaporation of the black hole on the gravitational side corresponds to the thermalization of the boundary state. Because the boundary field theory is a standard quantum field theory with no information loss. The information must be preserved throughout the evaporation process. The exact mechanism by which the information escapes the gravitational description is the subject of ongoing theoretical work. Recent developments in the past several years have provided new insights into the information paradox. The replica wormhole calculations, performed by groups led by Jeff Pennington, Ahmed Al-Mehri and others around 2019 and 2020, have shown that the information emerges from the black hole through subtle quantum gravitational effects that the original Hawking calculation missed. The new calculations reproduce the expected information preservation through specific gravitational path integral contributions that are themselves products of the holographic principle. No one expects, on first thinking about black holes, that the resolution of the information paradox would require fundamental insights about the structure of space-time itself. No one predicts that the careful analysis of black hole evaporation would lead to the conclusion that physical reality has a holographic structure. Absolutely no one anticipates the way the information paradox has, over 50 years, become one of the most productive areas of theoretical physics and the source of some of the most influential new frameworks for thinking about physical reality. Walk with me through what this implies for the broader theme. The information paradox is, in this sense, more than just a technical puzzle about black holes. It is a window into the deep structure of space-time and quantum mechanics. The resolution of the paradox requires holographic encoding of information on lower dimensional boundaries. The holographic principle, originally developed to address the information paradox, has implications for the structure of physical reality more broadly. The cosmos may, by every available indication, have a dimensional structure that is fundamentally different from the three-dimensional structure it appears to have. Hold this image. 50 years of work on the black hole information paradox, the development of black hole thermodynamics, Hawking radiation, the holographic principle, and AD-CFT. The recent replica wormhole calculations. The accumulating evidence that information is preserved through subtle quantum gravitational effects, encoded holographically. The cosmos is, by this work, revealing a deeper structure than the standard frameworks alone suggest. The hiddenness in this case is the holographic structure itself, which we are just beginning to map. What this leaves us with is a fifth truth that combines the other four into a deeper picture. The standard frameworks are missing specific things. They are also, in the holographic picture, possibly missing something far more fundamental about the structure of physical reality. The hiddenness extends from the specific parameters to the very dimensionality of the cosmos. The cosmos that contains you may, at the deepest level, be much stranger than the standard frameworks alone suggest. Tonight, we're going to spend a careful pass on what the five truths imply for the way you might think about your own existence, because the personal implications of being alive in a cosmos whose deepest physics is admitted to be incomplete are worth sitting with carefully. Before we get started, sit with the basic situation. You're reading these words in a particular body, in a particular room, on a particular night, in a cosmos whose foundational physics is, by the open acknowledgement of the best modern theoretical frameworks, missing substantial features. The atoms in your body are governed by quantum mechanics. The space around them is governed by general relativity. The energy budget of the cosmos that contains you is mostly made of substances we cannot identify. The fundamental constants that allow your existence have values that no theory can derive. The dimensional structure of physical reality may, at the deepest level, be different from what it appears to be. This is not a list of speculative concerns. This is the mainstream position of contemporary theoretical physics. You're alive in a cosmos whose deepest description is, by the careful work of the past several decades, openly admitted to be incomplete in specific and measurable ways. The first practical question is whether this changes how you should think about your own physical existence. The answer is no in the most immediate sense. Your body works the same way it always has. The room is still warm, the objects are still solid. The standard frameworks, despite their admitted incompleteness, are extraordinarily accurate for the kinds of physics that govern ordinary daily experience. The hidden physics operates at scales and energies that do not directly affect your daily life. No one expects, on first thinking about modern physics, that the deepest gaps in the theoretical frameworks would coexist with such precise descriptions of everyday phenomena. No one predicts that the cosmos could be both well described at ordinary scales and substantially mysterious at fundamental scales. Absolutely no one anticipates the way the modern theoretical landscape combines extraordinary precision with extraordinary admissions of ignorance, a slow turn. The second practical question is more subtle. Does the admitted incompleteness of physics change how you should think about the cosmos as the context for your life? The classical view is that physics provides the foundational description of reality, against which all other questions are eventually grounded. The modern view, taking the admission seriously, is somewhat different. Physics provides the best available description, but the description is openly incomplete. The actual foundational structure of reality is, in some specific senses, beyond our current grasp. This has implications for how to hold philosophical confidence about physical reality. The classical confidence was based on the assumption that physics was, in principle, complete. The modern admission is that physics is, in principle, not complete. The foundation is not fixed. The deeper structure remains to be discovered. Whatever philosophical positions depend on the completeness of physics may need to be held more provisionally than before. The third practical question concerns how the modern situation should affect your sense of awe at the cosmos. The classical view of cosmic awe was based partly on the size and complexity of the cosmos, and partly on the elegance of the physical laws that govern it. The modern view, taking the admission seriously, adds another dimension. The cosmos is awe-inspiring not just because of its size and complexity, but also because the careful work of investigating it has revealed how much of it remains hidden. The cosmos is, in this picture, larger in mystery than in mere extent. Expectation. Physics is finished. Reality. Physics is, in the most careful contemporary assessment, openly incomplete in specific and significant ways. What this means is that this is one of the more striking features of the contemporary situation. The same field that produced the Standard Model and general relativity, two of the most precise scientific frameworks in human history, also openly admits that 95% of the cosmic energy budget is unknown, that the two best frameworks are mathematically incompatible, that the cosmological constant is wrong by 120 orders of magnitude, that the fundamental constants are fine-tuned in unexplained ways, and that the dimensional structure of physical reality may be derived from a more fundamental holographic encoding. The precision and the ignorance coexist in the same field. The fourth practical question is whether being alive at this particular moment in the development of physics has any special significance. The honest answer is that we do not know. The hidden physics may be uncovered in the next decade through some unexpected experimental result or theoretical breakthrough. The hidden physics may remain hidden for centuries. Our specific cosmic moment is one in which the admissions have been made with unusual clarity. Whether the resolutions follow soon or take generations is genuinely open. Now, let's begin to think about what this implies for the broader philosophical context of contemporary life. The classical Enlightenment view was that scientific progress would gradually fill in the gaps in human understanding, with the gaps becoming smaller over time. The modern view, taking the contemporary situation seriously, is more nuanced. Some gaps have become smaller, other gaps have become more precisely characterized. The deepest gaps, the ones we have been walking through tonight, have proven remarkably stubborn despite intensive effort. The trajectory of scientific progress is not a simple monotonic narrowing of the unknown. There is, in this picture, a particular kind of intellectual humility that is appropriate to the contemporary situation. The standard frameworks are extraordinary achievements. They produce predictions of extraordinary precision. They also openly admit substantial limits to their own descriptions. The combination is, in some sense, more honest than either pure confidence or pure skepticism. It acknowledges what we have accomplished and what we have not. No one predicts, on first encountering modern physics, that the right response to the contemporary state of the field would involve simultaneous admiration for its precision and acknowledgement of its admitted gaps. No one expects that the most careful contemporary assessment would land in this particular kind of nuanced position. Absolutely no one anticipates the way the modern theoretical landscape requires this kind of careful, intellectual balancing. Hold this thought. You are alive in a cosmos whose deepest physics has been investigated with extraordinary care, and which has, in response to that careful investigation, openly admitted substantial limits to its own descriptions. The admissions are not a sign of failure. They are a sign of how rigorous the investigation has been. We know what we know to extraordinary precision. We know what we do not know with specific quantitative content. The combination is, in some sense, the most honest description of physical reality that humans have ever produced. What this leaves us with is a picture of personal cosmic existence that is, in some sense, more philosophically interesting than the classical version. You're alive in a cosmos whose physics is, by every reasonable contemporary assessment, openly incomplete. The incompleteness is not vague. It is specific. The 5 truths we have walked through tonight are specific cases of what physics openly admits it does not yet understand. Your specific cosmic moment is one in which these admissions have been made with unusual clarity. The future of physics will likely involve, over the coming decades and centuries, the gradual reduction of these admissions through new theoretical and experimental work. Whether you are alive to see the reductions, or whether they will take longer than your lifetime, is one of the open questions of contemporary intellectual life. Tonight we're going to address the 5 most common misconceptions about the limits of modern physics, because each one is widely repeated and each one deserves a careful correction. Now, let's begin with the first misconception. The misconception is that physics is in crisis. This claim appears in numerous popular articles and viral videos. It suggests that the standard theoretical frameworks have failed in some catastrophic way and that the entire field is on the verge of collapse. Expectation, the popular framing. Reality. The technical reality is that physics is not in crisis. Physics is in an unusually productive theoretical period, with many deep questions on the table simultaneously and substantial work being done on each. The standard frameworks continue to be used because they are extraordinarily accurate for the questions they were designed to address. The admissions of incompleteness are not failures of the frameworks. They are accurate acknowledgements of where the frameworks reach their limits. No one expects, on first hearing the popular framing, that the gap between the headline claim and the technical situation could be quite this large. No one predicts that the most widely repeated version of the story would so substantially overstate the actual scientific situation. Absolutely no one anticipates the way the popular framing of physics in crisis has, despite being technically inaccurate, become a standard feature of public discussion. Before we get started on the second misconception, sit with why the first one persists. Crisis is dramatic. It generates attention. Steady technical progress with specific acknowledged gaps is less dramatic but more accurate. The technical framing has, predictably, made less progress in the public imagination than the dramatic framing has. Now, let's begin with the second misconception. The misconception is that the admissions of physics mean we can never understand the cosmos. This claim sometimes appears with suggestions that the universe is fundamentally beyond human comprehension. The technical reality is more measured. The admissions specify what we do not currently understand. The specifications are precise. Each admission has been carefully characterized and is being actively investigated. The fact that we currently do not understand something is not equivalent to a claim that we cannot, in principle, ever understand it. The history of physics is full of examples of admissions that were eventually resolved through additional work. The takeaway is that this distinction matters. The popular framing of fundamental incomprehensibility forecloses on the possibility of future progress. The technical framing of current gaps remains open to future resolution. The technical framing is the more accurate one, and it is the framing that the working theoretical community actually adopts. The third misconception is that the admissions of physics support various non-scientific worldviews. This claim appears in various forms, often with suggestions that the gaps in physics validate religious, mystical, or other extra-scientific positions. The technical reality is that the gaps in physics are gaps in physics. They are not, in themselves, evidence for any specific alternative worldview. The various competing approaches to addressing the gaps, including string theory, loop quantum gravity, holographic frameworks, and others, are all themselves scientific approaches working within the broader scientific tradition. The gaps are openings for future scientific work, not concessions to non-scientific alternatives. Expectation. The gaps in modern physics validate alternative worldviews. Reality. The gaps in modern physics specify where future scientific work is most likely to produce significant progress, with the work itself being carried out within the scientific tradition. The fourth misconception is that the admissions of physics mean that previous theoretical work was wrong. This claim sometimes appears with suggestions that, for example, the cosmological constant problem refutes general relativity, or that the dark matter problem refutes the standard model. The technical reality is more measured. The standard frameworks remain extraordinarily successful for the questions they were designed to address. The admissions specify additional questions that go beyond the original scope of the frameworks. Adding new questions does not refute the answers we have for the original questions. The frameworks continue to be used precisely because they continue to work for what they were designed to do. No one predicts, on first encountering the modern situation, that the admissions of incompleteness would be compatible with continued use of the standard frameworks. No one expects that the same theories that openly admit substantial gaps would continue to produce extraordinarily precise predictions for the situations they cover. Absolutely no one anticipates the way modern physics combines acknowledged incompleteness with continued empirical success. Pause and notice. The fifth misconception is that the admissions of physics mean that the next theoretical breakthrough is imminent. This claim sometimes appears in discussions about new theoretical developments, with suggestions that the resolution of the various open problems is just around the corner. The technical reality is more cautious. The deep open problems of modern physics have been around for decades or longer. Some of them have resisted intensive theoretical effort for nearly a century. There is no guarantee that the next decade or even the next century will produce major resolutions. The work continues, with substantial energy and substantial resources, but the timing of any future breakthrough is genuinely uncertain. What this picture tells us is that this is a particularly important correction. The popular framing often suggests that breakthroughs are imminent because the gaps are well defined and the effort is substantial. The technical framing acknowledges that well-defined problems can still resist resolution for very long periods. The history of physics includes both rapid breakthroughs and centuries-long resolutions. The contemporary open problems may follow either pattern, and predicting which pattern they will follow is not currently possible. Hold this image: 5 misconceptions, each one widely repeated, each one wrong in specific ways. The corrections do not diminish the significance of the actual open problems in physics. The problems are genuinely significant. The investigations are genuinely productive. The standard frameworks are genuinely incomplete in specific quantifiable ways. But the popular framings, while attention-grabbing, do not accurately represent the technical situation. The technical situation is one of careful productive work on well-defined open problems, with the timing of resolutions being genuinely uncertain. What this leaves us with is a clearer view of what the limits of modern physics actually mean. Not crisis, not incomprehensibility, not concessions to alternatives, not refutation of past work, not imminent breakthrough. The actual situation is more measured, more interesting, and in some ways more honest than any of the popular framing suggest. The standard frameworks are the most successful theoretical descriptions of physical reality humans have ever produced, and they also openly admit the specific places where they reach their limits. Both things are true. Holding both things together is part of what it means to take modern physics seriously. Tonight, we're going to spend a careful pass on what comes next in the investigation of physics, because the various ongoing programs are worth knowing, and the directions of current work suggest where future progress is most likely to come from. Now, let's begin with the first major program, the CMB S4 experiment, a next-generation cosmic microwave background measurement facility being constructed at the South Pole and at the Atacama Desert in Chile, will provide substantially more precise measurements of the CMB polarization than the Planck satellite was able to obtain. The polarization measurements are sensitive to specific features of the very early universe, including the gravitational waves that may have been produced by cosmic inflation. If the gravitational wave signal is detected, the result will provide direct evidence for inflation and will constrain the inflationary parameters substantially. The CMB-S4 measurements will, in this sense, probe the physics of the very early cosmos in unprecedented detail. The second major program involves the LISA mission, the Laser Interferometer Space Antenna, which is being developed by the European Space Agency for launch in the 2030s. LISA will detect gravitational waves at much lower frequencies than the ground-based LIGO and Virgo detectors. The lower frequencies correspond to gravitational waves from much more massive sources, including supermassive black hole mergers and possibly relic gravitational waves from the very early universe. The LISA observations will provide complementary information about gravitational physics at scales that are not accessible to other experiments. What follows from this is that the third major program involves the various next-generation dark matter experiments. The Darwin experiment, planned for the 2030s, will use approximately 50 metric tons of liquid xenon, making it many times larger than the current LZ and Xenon NT experiments. The Cosinus experiment will use multiple target materials to test the Dharma modulation claim more carefully. The various Axion search programs, including ADMX upgrades and new approaches like Abracadabra and DM radio, will substantially expand the Axion parameter space being explored. The combined effect of these next-generation experiments will be a substantial improvement in our ability to detect or rule out the leading dark matter candidates. Let the idea breathe. The fourth major program involves possible future particle accelerators. The Future Circular Collider, proposed by CERN, would be a 100-kilometer circumference accelerator capable of reaching energies several times higher than the Large Hadron Collider. The proposed Chinese electron-positron collider, called CEPC, has similar ambitions. The International Linear Collider, planned for Japan, would provide complementary capabilities with electron-positron collisions at high precision. The various proposed colliders are expensive and politically uncertain, but if any of them are built, they will substantially expand the energy ranges over which we can probe fundamental physics. The fifth major program involves new theoretical work on the various open problems: the cosmological constant problem, the quantum gravity question, the matter-antimatter asymmetry, and the dark matter and dark energy puzzles are all being actively investigated by substantial theoretical communities. The work includes both new approaches and continued refinement of existing approaches. Progress in any of these areas could come from either experimental or theoretical directions, or from the combination of both. Step back, and you can see that the next 2 decades will be substantially more capable than the previous 2 decades for investigating the deepest open problems in physics. No one predicts the exact form of the next breakthrough. The combination of new experimental facilities, new theoretical work, and new computational capabilities represents a substantial expansion of what physicists can do. Whether this expansion will produce major resolutions of the open problems remains to be seen, but the work itself will substantially deepen our understanding. No one expects, on first thinking about the future of physics, that the next 20 years would offer such a substantial expansion of experimental and theoretical capability. No one predicts that multiple major programs would be operating simultaneously on the various deep open problems. Absolutely no one anticipates the way the next phase of physics may turn out to be one of the more productive in the history of the field. Walk with me through what this implies for the broader picture. The 5 truths we have walked through tonight are real admissions of current limitations. The next phase of physics will, with substantial probability, reduce some of these admissions. The reductions may come quickly or slowly, but the direction of progress is clear. The combination of new experimental data and new theoretical understanding will, over the coming decades, fill in some of the current gaps and probably reveal new gaps that are not currently anticipated. There is, in this picture, a particular kind of intellectual optimism that is appropriate to the contemporary situation. The standard frameworks have admitted specific limitations. The investigations of those limitations are active and well-funded. The next phase of investigation is being prepared. The trajectory of progress, despite the long history of stubborn problems, points toward continued reduction of the current admissions over the next several decades. The cosmos will continue to be larger than our descriptions of it, but our descriptions will continue to grow. Hold this image. The next 20 years of physics will involve substantial new experimental facilities, substantial new theoretical work, and substantial new computational capabilities. The 5 truths we have walked through tonight will be tested more carefully than they have been to date. Some of them will probably be partially resolved. Others may persist for further generations. The cosmos will continue to reveal itself, slowly and gently, through the patient work of the broader scientific community. What emerges from this is that this is part of why the current moment in fundamental physics is interesting. The combination of the long-standing open problems, the substantial expansion of investigative capability, and the active engagement of large theoretical communities has produced a particularly productive period in the field. The next breakthrough, whatever it turns out to be, will likely emerge from this combination of ingredients. We are alive at a moment when the careful work of the field is approaching the next major theoretical advance, even if the timing of that advance is genuinely uncertain. What this leaves us with is a sense of why the current moment matters. We are alive during one of the more capable phases of fundamental physics in its history. The work continues, the instruments improve, the theoretical understanding deepens. The hidden physics is being probed from multiple directions simultaneously. Whether the next decade or the next century produces the major resolution that the field has been working toward, the work itself will continue to contribute to our understanding in ways that go well beyond any single specific result. For the rest of the night, sit with the 5 truths we have walked through. 95% of the cosmic energy budget is made of things we cannot identify. Quantum mechanics and general relativity, our 2 most successful theories, are mathematically incompatible at the foundational level. The cosmological constant, predicted by the standard framework, is wrong by 120 orders of magnitude compared to observation. The fundamental constants of physics appear to be fine-tuned to extraordinary precision in ways that no current theory can derive, and the 3-dimensional structure of physical reality may, in the holographic picture, be a derived feature of a more fundamental 2-dimensional encoding that we cannot directly access. Each of these is a real admission from the standard frameworks. None of them is a fringe claim. Each one is taken seriously by the mainstream of theoretical physics. Each one has motivated decades of intensive theoretical work. The combined picture is one in which the standard frameworks openly acknowledge that they are hiding substantial features of physical reality, even as they continue to produce predictions that match observations with extraordinary precision. picture, for a moment, what this means for the cosmos you live in. The room you're in is filled by the standard picture with vacuum energy that the framework cannot calculate. The atoms in your body are governed by quantum mechanics, but they sit in a space-time governed by general relativity, and the two descriptions cannot be cleanly combined. The matter that makes up your body was produced by some process in the early universe that the standard framework cannot describe. The specific values of the fundamental constants that allow your body to exist have no derivation from any current theory. The very three-dimensional structure of your room may, at the deepest level, be a projection from a two-dimensional encoding that we cannot directly see. This is not a list of speculative concerns. This is a list of mainstream open problems in modern physics. The physicists who work on them are some of the most able and careful thinkers in modern science. The problems are not being ignored. They're being worked on with substantial effort. The progress, despite the effort, has been slow. Slowly, the camera in your imagination drifts outward. It leaves the room. It rises above the building, above the city, above the planet. It travels outward through the solar system, the galaxy, the local group, the cosmic web of galaxies. At every step, the same five truths apply. The cosmic structures at every scale are governed by physics that openly admits its own incompleteness. The galaxies are embedded in dark matter halos whose constituents we cannot identify. The cosmic expansion is driven by dark energy whose nature is mysterious. The fundamental physics at every scale, when examined carefully, points towards something deeper that we have not yet been able to reach. The camera continues outward. It passes through the cosmic web into the regions beyond the observable horizon, into the theoretical reaches where inflation may have produced other regions of cosmic reality. The same five truths presumably apply across all of these regions. The standard frameworks would, if applied to these regions, produce the same admissions of incompleteness. The hiddenness is not local, it is fundamental. The camera turns around and begins the long drift back, past the cosmic web, past the local group, past the galaxy, past the solar system, past the planet, through the atmosphere, through the city, through the building, into the room, to the foot of the bed. You are still here. The version of you in this room, on this night, in this particular body, is the version that is alive at the moment when physics is openly admitting how much of physical reality remains hidden from it. The cosmos is the cosmos. The hiddenness is the hiddenness. The implications are what they are. What this means for how you experience the cosmos tonight is subtle. The room around you looks the same as it always has. The objects are still solid. The air is still warm. The night is still here. What has changed is the meaning of what you are looking at. The cosmos you're observing is, by the careful work of modern physics, a cosmos whose deepest structure is acknowledged to be missing from our best descriptions. The cosmos is not different from what you have always known. The story we tell about the cosmos is different. There is in this picture a particular kind of philosophical interest. You're alive at a moment when physics is openly admitting what it does not know. Every previous generation has had its own gaps in understanding, of course. What is unusual about the present moment is the precision of the admissions. The standard frameworks do not just admit ignorance, they quantify it. The cosmological constant is wrong by 10 to the 120. The fine-tuning conditions span specific numerical ranges. The information paradox has specific mathematical content. The hiddenness is, in this sense, precisely characterized rather than vaguely acknowledged. There is no need to hold all of this in your mind. The five truths will keep their shape whether you remember the details or not. The standard frameworks will continue to be used because they are the best available. The deeper physics will continue to be worked on by the theoretical community. The progress when it comes may be gradual or it may be dramatic. Either way, the work continues. The cosmos that contains your sleeping body is, by every available measurement, a cosmos whose deepest physics is admitted to be incomplete. The admissions are not a sign of failure. They are a sign of the empirical rigor that has produced our current frameworks. We know what we know, and we know what we do not know. The known things are extraordinary. The unknown things are vast and specific and currently beyond our reach. Sleep can come whenever it wants now. The story has done its work. The cosmos that contains your sleeping body is the same cosmos that contains the dark matter, the dark energy, the quantum gravitational regime we cannot describe, the fine-tuned constants whose values we cannot derive, and the holographic encoding whose surface we cannot see. You are part of it. The hidden physics is part of it. The work of discovery continues. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.